Bringing us back to impulse and momentum. One application of that is follow through. So in most sports, they ask you to follow through with different things like throwing, kicking, hitting. Okay. So if you didn't follow through, let's say I didn't follow through kicking this ball. Like I kick it, but I don't follow through. What that's going to look like is my foot stops when it touches the ball. The way to do that physically is to essentially kick the ground. Okay, so when I kick, okay, I didn't really stop, but much. But versus if I follow through, I'm not going to kick any harder. I'm just going to follow through. What was the difference besides it was a harder kick? Like why did it do what it did? Physics wise. Why is follow through important? You do end up with more momentum. Why? I like that. Why do you have more momentum? What gives it more momentum? You apply the force for a greater period of time. Does that make sense? Now, you might be thinking, oh, that's not that much more time. That's true. Not that much more, but it was a substantial difference. The nice thing about today, we've got access to a bunch of videos like slow motion stuff. Here is a tennis ball being served by or hit during a serve of tennis racket. Oop, nope. And then taking it frame by frame. Right here is where the tennis ball starts experiencing a force. Here's where the tennis racket would stop if there was no follow through, but notice how much more time there is for the follow through. Right about there is where the tennis ball leaves the racket. So it's about twice as much time. Okay. Going to run through this again. Just notice the jello effect of the tennis ball. So cool. Okay. All right. Different scenario. Talk to your neighbor. Tell them why you think so.
Oh, but time also no, but time. But time is that could be anywhere. Wait, oh, impulse? Are we? Wait. Impulse is changing momentum. Oh yeah. Okay, so then it does have like a could not go over. But this will be greater. Yeah, so it's just because it's only because it takes more time to stop, but it goes back. Oh, right. Like it goes on more. But the velocity of it is are we looking at the first of the car? Yes. It's the same. I think it's are we looking at the force or
On the car. Looking at the car. Yep.
So
Okay. Correct answer is okay. The definitive approach to answer this question, we're looking for the change in momentum. Here, this is definitive. They have the same mass. They both experience the same change in velocity. Therefore, they both experience the same change in momentum. Doing this route is really fuzzy. Like, but this route, same mass, both started at 60, both stopped at rest. Good with that? Okay. Now, these next videos are kind of reenacting this. Here's the brick wall. Okay. The haystack. I don't know if many people run into haystacks. Like Back to the Future. I don't know if you've seen that movie, but that's like, anyway. This is more realistic. So you ever seen these barrels in front of, like on the interstate? You have an overpass. You got the center concrete column that holds up the overpass, holds up the bridge. And they have these yellow barrels. They're either filled with sand or water. Okay, that's going to simulate our haystack. Same scenario. Tell your neighbor. Which one changed its momentum in less time? Correct answer is A. Brick wall changed its momentum really fast in a small amount of time. Same scenario. Tell your neighbor. Okay. Correct answer is A. Now, both the brick wall and the haystack of the car, when they hit, both of those experienced the same change of momentum. But the end result is drastically different. Okay. You get a truck that looks like this. Nope. Here's brick. Oh, truck that looks like that. Look how short that is. Versus a truck that looks like this. Because the brick wall changes the momentum in a really small amount of time, that required a huge amount of force. Versus the haystack gave more time for the momentum to change, which required less force. You all right with that? Okay. Here is another way to think about it. So velocity is equal to the change in position over change in time. Another way to say that is the rate at which position is changing. You okay with that? The rate at which position is changing. If we divide by time on both sides, what we get is this. The net force is equal to delta P over delta T. This quantity is the rate at which momentum changes. The rate at which momentum changes. And this is actually how Newton wrote his second law. Not force is equal to mass times acceleration, but then force is equal to how quickly momentum changes, the rate at which momentum changes. Okay. The car that hit the brick wall, changes momentum very quickly. Required a large force. Okay. Last question on this scenario. Tell your neighbor. Correct answer is C. They both experience the same change in momentum, therefore they experience the same impulse. Force, the quantity of force multiplied by the time that force was applied is identical. It'd be really hard to figure out from this way, but you know from this, that's equal to that. Good there? Okay. And there's Oh yeah, there. Okay. Tell your neighbor. Correct answer is what are you missing? Time. You can figure out the change in momentum, yes. But you do not know the force because you don't know how quickly that momentum changed. You don't know the time at which it took that momentum to change. With that, you can figure out, you know the impulse, but that's not the same thing as force. Talk to your neighbor.
Isn't no.
What hour do you need to pass for?
I don't need a pass because I don't have a 10th period.
Ben, when you need to pass?
Yeah, 10th
Welcome.
I should.
Okay, what do you say? All right, so which one changed its momentum more quickly? One way to look at it is to say this is the rate at which momentum is changing. So the one that experiences a greater force experiences a greater rate of change of momentum. Or you can say they both experience it for the same time, but the one that has a greater force experiences a greater change of momentum. Correct answer is A. Okay. The motorcycle definitely sped up faster. Totally agree. But the change in velocity is not the only thing that is captured, described by momentum, change in momentum. You also have this mass factor. Okay. So the truck experienced a greater change in momentum, or rate of change in momentum, because it experienced a greater force. The engine was more forceful. Okay. Both experienced the same. Sorry, both experienced their respective forces for 5 seconds. The truck had more force, therefore it experienced a greater change in momentum. No, change in velocity is not the same. The motorcycle would be will have a like acceleration of 10 times the amount. Oh no. Uh-oh. Shoot, I've been telling the kids this whole time. Wait a minute. Oh no. No, I'm right. Totally right. The change in velocity is the same. Change in velocity is the same because they have the same acceleration, because they have the same ratio of force to mass. Man, I made that easier. Okay. That is unrealistic. Anyway, even if this is like twice as much force, and the truck speeds up slower, which it does in real life, the Mack truck will still experience a greater change of momentum because it experiences a greater force. Yeah. Yep. Yep. All right. Okay, Newton's third law. We talked about it ways back, but I want to make a more formal definition. You might have remembered Newton's third law from junior high physical science, which in junior high you would say for every action there is an opposite and equal reaction. I don't know if you heard that, Newton's third law. For every action there is an equal and opposite reaction. I am not a big fan of that. but taking a test right now. Oh, lab. Just grab a mass set. It's on the side of the wooden set of masses. Right here.
This.
Yeah. All right. So, not a big fan of for every action there's an equal and opposite reaction because it describes things that aren't Newton's third law. What goes up must come down. Equal and opposite reactions, not Newton's third law. Okay? Not Newton's third law. If I hit you, you hit me back. That is not Newton's third law. So here's a better description, in my opinion. This is my homebrewed description. If object A exerts a force on object B, then object B simultaneously exerts a equal force back on object A in the opposite direction. There it is. It's a mouthful, but it is more descriptive. Object A exerts a force on object B, and object B simultaneously exerts a force, an equal force back on object A in the opposite direction. Yeah. Measure this one. Connect those two. Hang that.
So just this one, these two.
Yeah. All right. So that is Newton's third law in all its glory. So let's look on how to apply that. Okay. As you kick a soccer ball, the foot exerts a force on the ball. Applied for it, you're like, okay. So based off of Newton's third law, if the foot exerts a force on the ball, then the ball simultaneously exerts an equal force back on the foot in the opposite direction. So this would be Newton's third law. Okay, there's an equal force on the foot from the ball. Now, you might be thinking, that's stupid. Like, the ball is just sitting there. The ball's the perpetrator. The ball's the one that's at fault. The ball's the one exerting a force. No. The foot's the perpetrator. The foot's the one exerting the force. Like, how is the ball exerting a force on the foot? Have you ever like whiffed a ball before? Like missed it completely, like trying to hit, and you're like, "Whoa!" Did you know you missed? Why? Because you're expecting your foot to hit something, to experience a force back on it. Okay, Lexi.
That doesn't make sense though, because the ball would be moving, but if the forces are equal to zero, then that's
Excellent question. Hang on to that thought. I love that thought. All right, so if I'm pushing on a refrigerator, it's pushing back on me. Because if the refrigerator wasn't there, you want, like, you're ready for that force to come back on you. Okay, if you're so the chandelier experiences a tension upward, suspending it. If you're part of that chain, a link in that chain, you're gonna be feeling that tension going down. You're like, oh, this thing's so heavy. Okay, here's the weirdest one. As the raindrop falls, there's a force of gravity on the raindrop pulling it downward. Everybody's okay with that? Okay. What is the object that creates or causes gravity? We haven't really studied this yet, but the fact that the Earth is so massive creates gravity, causes gravity. So, what are the two objects that we're looking at here? Object A is the, object B is the. So if the Earth exerts a force of gravity on the raindrop, then the raindrop, see if you can complete that sentence. Exerts a force of gravity on the Earth. Oh. Whoa. What? What? No. Wait a minute. So you're just telling me so I'm jumping. Gravity pulls me down. I experience acceleration of 9.8 meters per second squared. Everybody okay with that? But what about, like, you're saying are you saying the Earth comes up to me at 9.8 meters per second squared? That's what you're telling me? To get the right answer on the test, I'm going to say yes, but my common sense says no, that's just absolutely ridiculous. The acceleration is not 9.8, but the force of gravity acting on the Earth is equal to the force of gravity it's pulling down on me, based off of Newton's third law. So, why is the Earth not experiencing an acceleration of 9.8 meters per second squared upward? Like, quit jumping! Oh, quit jumping like you're shaking. Like, why is that? Why am I not causing mass destruction right now, like as I'm jumping? Because it experiences the same force as I experience going down. Why is the Earth not accelerating upward at 9.8 meters per second squared? Guesses, thoughts, anybody? Talk to your neighbor. Any brainstorms? What's more massive? the Earth a little bit more massive, like astronomically more massive. Okay, so we experience the same force, but the acceleration of the Earth, the acceleration of gravity from the Earth is so infinitesimally small that it can't even be measured. Good with that? Okay, weird, I know. All right, here are some characteristics of Newton's third law of force pairs, sometimes called action-reaction force pairs. Okay, they always have the same magnitudes as each other. Always same strength. Always. Act. Act in opposite directions. Well done. Thank you. Always act simultaneously. Can you pass? Boom. All right. There's the characteristics. Where are you going, Angie? Welcome. Okay, good with that? Newton's third law. It's just another way to describe that. All right. So we've talked about these four the first four characteristics. You have simultaneously opposite direction, same magnitude, different objects. You have object A and object B. Okay. But they never cancel each other out. Lexi, this is hitting what you were asking. Okay. The reason why they don't cancel each other out is because these forces act on different objects. In a free body diagram, this force can't ever cancel out this force because they're acting on two different objects. In order to cancel out a force, the forces need to act on the same object. These two forces could cancel each other out. But this force and this force cannot. Like, impossible. Act on two different objects. Good with that? Okay. All right, for this scenario, I want you to draw the free body diagram of block A and block B separately. Two free body diagrams, block A and block B. And then answer the question. Talk to your neighbor. Correct answer is? Got a vote for B. Got 2 votes for B. D. Vote for D. Normal force.
Wait, what kind of
Normal force.
that B pushes that way? I'm like so confused. And you're like 2, and I was like, why is it acting that way?
Because it's touching it.
What did it act?
There's 2 normal forces. So here, this one experiences a force, a normal force on B from A. This one experiences a normal force from the ground. This one has friction and force of gravity on B. This one has an applied force from the hand. You have a normal force on A from B. You've got a normal force on A from the ground. And you have a force of gravity. Oh, let's see, there's another one. There's friction as well. And there's force of gravity on A. That's the free body diagrams. Okay, so what this question is asking is how does this force here compare with this force here? That's what this is asking. Correct answer is D, the same. Okay, due to Newton's third law. Okay, follow-up question, same scenario. Correct answer is D. Okay, they act on two different objects. They do not cancel each other out. They act on two different objects. Okay, now if we switch A and B around, for the sake of time, are we okay with the fact that they still exert the same force on each other? These might be different than the first scenario, but compared to each other, they're the same. Good with that? Talk to your neighbor. Okay. Correct answer is C, the same. Follow-up question. I don't know why people are backing up. We still have 3 minutes. Acceleration. How do they respond to the force? Okay. Now, this, I could tell you the right answers when I was in your shoes, but I didn't really believe it until I saw this demonstration. Not what I want. What I've got is I've got two things that are going to crash into each other. Okay. What I have. Oh, give it to me. Isn't that crazy? Okay. Okay. What I have is this. I've got two force probes. Come on, baby. Why ain't you working? That's not good. No bueno. Go faster. Come on. Ah! Acceleration was bigger for the Volkswagen. See it.
Be here for finals week. Sorry.
I leave the Saturday after final, like after the first final.
Oh dear.
Yeah.
Okay.
When do you want me to take it? Do you want me to take it before I leave? After? Please don't say after.
Let me think. That's rough.
It wasn't up to me. My parents were like, "We're going on vacation." I was like, "Oh, that's finals week. I'll be here."
That's a kick.
I gotta take my test today. I'm gonna fail. You'll be fine.
Let me chew on that.
Okay. This is right.
Come up with a proposal for me.
Okay, I'll figure out it.
My sister, she didn't know, and she got like, would it be possible to do it like after school? Is that a possibility? Okay. I'll just figure out. She would do it all on that part because she said I had no idea what to start. I felt like.
Okay. Do this. Ooh. All right. Here's what I'm going to do. These two things are, we're going to do multiple different collisions. We're going to do rear-ended. We're going to do head-on collision. We're going to do this pushes this, and then this pushes that. And we're going to look at the graph after I do this. Collision, rear-end collision, head-on collision, push, push. Okay. And then oh, I hope this works. Nice. And as you can see, not like in real time, but I just made this graph on the same computer. So as you can see, you have the same forces acting in opposite directions during the same time. This is the crash, this is the crash, push. Okay, so they have the same force, they just react differently, of course, depending on the mass.